Welcome, physics friends, to 22.2, which I have entitled Electrical Current. So we're going to get away from static electricity, which is still and stagnant. You're building up charge, moving it. Now we're going to be continually pushing charge around in what's called a circuit. So you're going to learn today about circuits. You're going to learn about Ohm's law. That's the law that governs how much electricity runs through circuits. You're going to learn how to find power. We're going to learn about schematics. So there's just a few things that we're going to learn today. And I'm going to teach you about what's called the water analogy. Everything in electricity can be modeled with water. So here we go. I'm going to take you over to the PhET website. This is an interactive thing, and I'm just going to build a very simple circuit. So I'm going to grab a battery. I'm going to grab a wire. And I'm going to grab a light bulb. And believe it or not, every circuit needs three things and only three things. You need a voltage source, like a Van de Graaff generator, a capacitor, a photo cell, photoelectric, solar panel. You need a conductive pathway. In a lot of electrical properties, electrical applications, it's a wire. And then, with us, we grabbed hands in a circle. You can touch, the human body can be a conductive pathway. And then you need what's called a load. And a load in this case is it's the light bulb. Resistance. This is the trickier part. Now the thing is, if you don't have a load, it'd be like going from bench pressing 300 pounds to then bench pressing 0. If you don't have something to resist you, you can push too hard and bad things happen. So watch what happens when I take away the load and I just hook the wires up so it starts on fire. This is what we call a short circuit. A short circuit, it's short one of the three things. You're supposed to have a conductive pathway, a voltage source, and a load. If you don't have that load, you're short one of the things and it creates smoke, fire, maybe you've seen sparks. But when electrons flow, it creates heat. So you need to have some sort of load in there. You can put a resistor in there also. And that resistance, I can change the amount of resistance. If I have more resistance, I slow the current down. If I have less resistance, I can speed it up to where I have 0 resistance. So let's go back to our circuit and let's talk about the things it needs. Circuit. It's a closed loop of electrical current. And it needs to be closed. If it's not, if I go back here and I open this up, I cut it, the electrons need to work their way back around to the positive side. Like that. So if it's not closed, if it's open, we call that an open circuit. And we have special devices that will open and close circuits. They're called switches. Put myself a switch in there, close my switch. That's what they call it. Call it closing the switch. You've closed the loop of current. You can open your switch. That's open. There's no longer a loop going on. A closed loop of circuit. Current. You need three things. A voltage source. A conductive pathway. And a load. A short circuit. When the load is skipped or missing. And in our case, remember this simple circuit that I drew. And you don't need these things every single time. But the simple one that I did, the voltage source is the battery, the conductive pathway is the wires, and then the load in this case was the light bulb. Let's go back, we'll define a few terms. You've maybe heard these terms in your day-to-day, but we're going to define them pretty specifically now in a physics sense. Charge. That's basically the number of electrons. The units are coulombs. And in an equation, you'll see it as the letter Q. And you've seen this before in static electricity where it's Q1 times Q2 divided by the distance squared. Voltage. This is a new term for us. Voltage is like pressure. Let me go back and I'll just show you these first, and then we'll define them. So here's my voltage, and you can see down here when I click on my battery, I can adjust the voltage. So it's like pressure in that if I increase the voltage, you'll see that more and more current flows. So if I have too much current, the wires can't handle it, and then they can melt and light fires. So this is why in your walls, you have to have, depending upon how much resistance is there, what device you're plugging in, too much current can flow and then start your house on fire. So you have to have certain wires rated for certain amounts of current. So the more pressure you have, the more electricity flows. Pressure. The units are pretty clever. They're volts. And in an equation, you're going to see the voltage with the letter V. This is the best one. Current. That's amount of electrons per second. Its units are going to be amps. In an equation, you're going to see it as the letter I. This one is crazy. It's all different. Current, it's 1 coulomb per second. That's what 1 amp is. So going back to my example here. So the number of electrons per second, that's current. And I can actually measure that with this guy right here. I can put this into my circuit. It measures current. So there's 3.8 amps. If I up the pressure, you'll see that my current goes up. And if I up the resistance, you're going to see this in a second. The resistance is like a kink in the hose. If you add resistance, if you kink this hose, then you can have less water flowing. So if I increase the resistance, you'll see that my current goes down. And you can see these colors are all changing. There's a little color code that tells you exactly how much resistance is there. 25.5, there's a color code, and I'll teach you that in a little bit. But just so you know that current is related to voltage and resistance. So resistance. The opposition to current flow. Its units are going to be what are called ohms, O-H-M-S, and it's the Greek letter omega. In an equation, it will be the letter R. So that one's kind of nice. Sometimes you'll see ohms written like this. I said it was the Greek, it's like an upside down horseshoe. It's a Greek letter, capital omega. Energy. That is the currency of the universe. Get in here. Energy is, we traditionally define it as the ability to do work. That means create heat, create light, lift something up in the air. Its units, you probably already know, you just didn't know that, are joules. Maybe you remember back to thermodynamics. Joules are energy, how much heat that you have. So in electrical terms, all electrical devices create heat. So we'll be using energy quite a bit. In an equation, you'll see it as the letter E for energy. And then power. Power is how much energy you can produce per second. Like lifting up 400 pounds in like a squat. How fast you do that means that you have more power. So that's the time rate of energy. Its units are going to be watts, sometimes known as a joule per second. So if you have 1 joule per second, that's what a watt is. A watt is a unit of power. In equations, you might not be able to see this because my thumbnail's in the way. In equations, it's used the letter P. So P stands for power. E stands for energy, R is resistance, I is current, V voltage, Q is charge. So you kind of can see this, most of these things when I go over here. Voltage, that's like pressure. If I increase the pressure, I can increase the current. Resistance, that's like a kink in the hose. If you increase your resistance, less and less current flows. So current, it's directly proportional to voltage or pressure. It's indirectly proportional to the resistance. So more resistance, less current. Less resistance, more current. That's what indirectly proportional means. Voltage, it's directly proportional. More voltage, more pressure, more current. Less voltage, less pressure. Less voltage, less current. So they're directly proportional, indirectly proportional. That's how current is related to voltage and resistance. Now there's a water simile. A water simile, I guess you could say, or a metaphor. Electricity is like water, and voltage is like the level of water. So if you had a tank that had more water in it, it's going to have more voltage and more pressure pushing down on it, which is going to squirt more water out of it. So the more pressure you have, the more water can flow. Now, resistance. I told you before that resistance is kind of like there's a rock lodged in here, but you could like put a kink in the pipe, right? And you can kink this pipe in lots of different ways. You can kink it here, you can kink it here, and then you can kink it a lot right there. So these kinks are all going to add up, and they're going to limit how much current flows through it. So the more pressure you have, the more water squirts out. The less pressure you have, the less water comes out of this. The more kinks in the pipe, the less, and you can turn it on and off with the faucet. Everything in electronics is there's a really good metaphor in the water world to help explain what's going on. Next, we're going to talk about what's called Ohm's law. Ohm's law says this. It's voltage, how much current is available. How much current, remember it's in amps, it's directly proportional to the voltage, and indirectly proportional to the resistance. This is what's known as Ohm's law. It's probably the single most important equation that you'll ever see in the electrical world. All of us use this on a daily basis to figure out how big of a resistor should I use? How thick of wire should I be having? Like, I use this constantly when I'm doing anything electrical related. Power. There's a power equation. It goes like this. Power is equal to the current times the voltage. So P is power. And remember, that's in watts. I is current. So I'm just going to draw this one down. And then V is volts. Some people, you can actually combine these two equations. So you can use substitution, and you can take this I times R and put it in for V. So sometimes people will write this. Power is equal to the current times voltage. Or it's power is equal to I squared R. So you can combine those two things just depending upon your needs for the equation that you have. There's one more equation that I didn't list here, but I just wanted to show you now, like energy. We talked about energy before, how power is equal to energy per time. So power, P is power, E is energy, which is joules, and T is time in seconds. So we get going through these, three equations pretty quickly. So you just got three more tools in your toolbox. And let me give an example of how I would use this. This first one's kind of an insult to your intelligence. It says there's a 6-volt battery. It delivers 5 amps of current to an electric motor across its terminals. What's the power? So you're going to, power is equal to the current times voltage. So current, voltage, insult, 6 times 0.5 is 3 watts. That's part A. Part B, if the motor runs for 5 minutes, how much electrical energy is consumed? So part B, I'm looking for energy. So I'm going to use power is equal to the energy divided by the time. So my power, 3.0 watts, how much energy? And my time, you can't use 5 minutes. You got to use 600 seconds. Well, 5 times 60, 300. Oh, I'm having a brain fart here. 5 times 6 is 3,300. So when you multiply these, 300 times 3 is equal to 900. That's 900 joules, like that. That's how much energy that you just consumed. Now, the last thing I want to talk to you today, well, one other thing, what affects resistance? So a wire, there's a lot of different things that affect how much resistance can occur inside of a wire. A longer wire has more resistance in it than a shorter wire does. And this is actually how, maybe you've noticed in my classroom I've got this like variable resistor. It's actually just a big long wire that's been curled, and I'm touching different parts. So I'm sending the electricity through different lengths of wire, so it has more or less resistance. The thickness of it, a thicker wire has less resistance than a thinner wire. The temperature affects how much current flows too. And maybe you saw this with liquid nitrogen. The colder something is, the easier electricity can flow through it. You know, and Mr. Hare, why doesn't my car like to start when it's cold outside? Shouldn't that be good because cold is better? Cold is good for wires, but it's not good for batteries. So you're having a problem with your battery. The wires love being cold. Electricity you can actually make things superconducting if you get them cold enough. And then again, what type of material? So we talked about in static electricity, what makes good conductors with copper and gold. You know, platinum has more resistance than copper and silver. Those are good resistors. They have conductors, I mean. One last example problem. It says a 30-volt battery is connected to a 10 ohm. See, there's that symbol again, that omega symbol. That means resistance. What's the currents? So we're looking for current. I equals question mark. We've got a 30-volt battery, so the voltage is equal to 30. And then the resistance, I'll just use R, is equal to 10.0 ohms. So there's an equation that links all these things together. V equals IR, which is Ohm's law. Voltage being 30. Current being 10. Oh, insulting. Resistance. Nope, sorry. Resistance is 10. Current unknown. So 30 divided by 10 is 3. And that's amps. You're literally having 3 coulombs pass by you per second. And remember that a coulomb is a lot of electrons. It's 6.24 times 10 to the 18th electrons. So you're having 3 times this amount going past you every second. So as even though I use this demonstration here, to kind of help you visualize currents, like this is truly not what it is. Like there's so many electrons, like quintillions of them traveling, but it's easy to see in the human perspective when you see it like this. All right, kids, that's enough of me talking at you. So this is what we call Ohm's law. Oh no, I have one more thing. I'm sorry. I forgot about our schematic symbols. A lot of times inside of when we make circuits, we use symbols. So here you see, here's a simple circuit that I made. I don't have to be a cartoonist to draw this every single time. What you're going to do is use symbols for all of this stuff. So a battery is going to be like this. So I'm going to go long, short, long, short. Actually, I should probably do this backwards because the long one means is the positive. And I know on batteries that this is the positive side and this is the negative side. I've got a resistor here, so I've got a wire. And a conductor is just a line. And then a resistor here is a squiggly line, a fixed resistor. So I have a squiggly line. And then I've got a light bulb, and a light bulb looks like this thing right here. So I make a loop and I circle it like that. My light bulb, I come around, I have a switch. And a switch looks like this. So it kind of, you can see how it would fold down and make contact. So here's my switch. So there's a schematic representation of this simple circuit that I made a little bit earlier to show you how schematic symbols are used by engineers and technicians to show what's happening versus what it actually looks like. I've got a few more questions that we'll probably do during class in the coming day. So that's why these are stuck on the end. All right, friends. That's enough for me for today.